All right, folks. Sorry for the 1 minute lateness. Promise to give you that back at the end. So I think, and this is a conversation that was started before we started recording. We are headed in a really fun and interesting direction. Because tensors, in my opinion, are not obvious. And we're learning sort of the rules of how to use them. And as you learn the rules of how to use tensors, it's a little annoying. Maybe if you like math, you prefer that to the physics that we tend to use. But I think that the best application for tensors that you've never seen before is general relativity. Now you've heard the words general relativity, but you maybe don't know what the fuck that means, right? So general relativity describes the curvature of space and time itself due to gravity. And it's beautiful, it's gorgeous. But you need to know how tensors work in order to use it. So what I'm trying to do, and I will attempt to the best of my abilities, is to weave together, say, a week of how to use tensors, which is what we'll finish up today. I don't know if we'll get as far as I wanted to. We didn't quite get as far as we wanted to last time. And then I'm going to start injecting a tiny bit of special relativity in the context of understanding why you need tensors to do these types of things. So questions like the invariance principle for all of physics. That is to say, if I take a measurement in one set of coordinates, it should be the same in a different set of coordinates, right? Under certain conditions. Okay. So we'll apply that in the context of these tensors, which are making up how we describe measurements in the first place. And interestingly enough, we will apply certain operators to those tensors, and then we will become familiar with how operations appear on tensors, and we'll try to apply them to the curvature of space-time itself. That seem reasonable? So we're going to kind of go back and forth between your BOAS book and applications thereof that are found in Hartle and or at the end of your Jackson, what did the book use? Griffiths. Use Griffiths for E&M. So the last chapter in Griffiths for E&M describes special relativity and doesn't even touch general relativity. And so what I'll try to do is I'll try to weave some of that in there, and we'll talk about this thing called 4 vectors, which you know is just a vector with 4 components. We'll talk about what the fuck that means. And then we'll use it in the context of general relativity when we talk about something called metrics and Hilbert spaces. Is that okay? Have your buy-in on that? Okay. And if it gets really horrible, you're like, what is going on here? Let's go back to fluids, because we can always bail, right? We can talk about those spaces, and then we can say, actually, this is far too complicated. Let's instead talk about fluid dynamics, which also uses tensors, or we could even talk about the Maxwell stress tensor, which is discussing how electric and magnetic fields generate, right, due to charges, charge distributions, I should say. Okay. Okay. So let's just warm up the brains. What are the words that we came up with last time? We said something like a tensor. What was that thing?
There was a tensor.
No, just what's a tensor?
Oh, tensor.
We give a definition for that? Or did I just say a bunch of things are tensors?
It should be like n-dimensional data set.
Okay. Okay. For n to be 0, right?
Yeah.
Yeah. Okay. It'll have certain properties that we'll try to explore today as well. It has to do certain things to be considered a tensor. But we haven't discussed that yet. Tell me about a matrix. What's a matrix? A second rank tensor. So what's that word you just used there? What does rank mean? How many what? How many indices what? That it has? Yeah, I would modify this slightly. How many indices are required in order to tell you where the element is? Right, so for a scalar, you need no indices because it's a single number. For a vector, you need at least one index, because you have to know where in that space this thing exists. Like you said, in a second rank tensor, you need to know its row and its column. And a third rank tensor, you need to know its row, its column, and its depth, right? And for fourth rank tensors, well, we just don't have an intuitive feeling of those, right? So we don't live in a four-dimensional space. That doesn't mean those spaces don't exist. We just don't occupy them, right? Okay. So everyone's brain is warmed up then? Okay. So let's go back to the idea of what the motivation for some of this was in using tensors in the first place. We wanted to say something very specific. We wanted to say something along the context of physical results that we find in the world have to be independent of coordinate system. And if that's the case, then there are specific physical quantities, right, that don't care about the coordinate system in which you're found. Is that reasonable? That's just the corollary of that same statement. Okay. So let's start with something called a change of basis. Okay, so what does basis mean here? Basis is simply your coordinate system. You're going to use all sorts of new fancy words because language matters, right? And when we talk about these things in a more general aspect, it's really important not to get bogged down thinking only in terms of Cartesian and spherical, which is what we're used to, when there's many types of geometries that we're going to do, particularly when you get thinking about four-dimensional geometries, which we have no internal feel for, right? Okay. So when I say something like the change of basis, what does that mean?
That it means that the change of coordinate system, so going from like Cartesian sphere.
Exactly right. So that would be going from cart to spur, right? For example. What would be another way? Say, don't trade coordinate system. Is there anything else you can do?
You can kind of shift the coordinate system.
Good, yeah, you can move it, right?
Yeah.
What are the types of moves you can do? X to the Y, what does that mean? There's a word for that, right? Here's my coordinate system.
Yeah. Well, you can like invert it or?
What do you mean inverted?
No. Because my original thought was just like, oh, you can take the x-axis and then like shift it like a couple like units to one direction, and you can do that for every single axis.
Okay, good. So that shifting is called
Translation.
translation. Very good. Okay, so you can do something like shifting. The appropriate term there is translation. And of course, we know that translation comes from ancient times. It's a Galilean transformation. Galilean, no, sorry. Transformation. Okay, that's one. What's another example? Rotation, very good. So that's what you meant by X into Y, right? But we want to make sure we're using the right terms there, and you can do rotations as well, right? And there you haven't necessarily changed the style of the coordinate system, but you still have changed the basis. Okay, so that's really important. We're going to describe a set of basis vectors. Okay, so we're going to say that basis vectors E1, E2, and E3 describe, and remember, we're still working in three dimensions there, are 3D space. Okay? Anyone hate that choice of notation? No. So why am I not using X, Y, Z?
Because it could be in any coordinate system.
Doesn't mean any coordinate system, right? And remember, we already said we're getting rid of X. X no longer, or sorry, we're already getting rid of Y and Z. Only X exists, and it exists in the context of Xi, right? So if you want the different components of your vector, it's Xi, which would be X1, X2, and X3. Similarly, our basis vector here can represent any physical space, and we're using E to describe it. So you might say something like this. How would you write that in terms of our new notation?
Would be, I think
You're close because I like the first one, X what? X1.
and then E1, like. E1 plus X2, E2.
Yeah, and I'm gonna actually do this, if that's okay? Is that okay? How else could you write this? Remember, we're working in the new tensor math world.
What, like XI, EI?
Very good. Why is that the same thing?
That, like, when you multiply it, like, those two together, like, with tensor math, it's like, that's the same as summation, because it becomes, sum.
Exactly right. Isn't that interesting though? So typically what you would write here, you know, you might do something like this. When you were a child. Right? And that's just ugly. Look at how much more beautiful that is. I can take this whole vector here, and it's simply represented by this. In the dual notation. Right? Dual indexing notation. Okay. We can say a couple other things here. Don't know how much we want to go into it. I think we want to just start talking about Cartesian coordinates and then use one of them to describe what the importance of them is here. Okay. So let's start over here. And we're going to talk about a particular class of coordinate transformations. The easiest one to discuss is the rotation transformation. Okay. Yeah. Do you guys know how to build one of those? Rotation matrix, without looking it up,
Right.
Anyone can look it up. I'm just curious if you have an intuition for it. It's okay if you don't.
For like a matrix.
Yeah.
Yeah, so it's like you build a matrix, and like they're,
It's like, that's like the like a 3x3 and then you like, I wanna say the transpose, but I don't remember the matrices very.
there's,
Okay, yeah, so there are some interesting words in there. So transpose, what does that mean?
It's not. It's like when you flip the thing.
Good. It's when you flip the thing.
Yeah.
No, and this is actually really important because that is what it is. And it's sometimes important to just build a mental model. Okay, so let's imagine that I have a row here and a row here. Column here, column here, column here, column here. And let's call that T. What does T transpose look like? That's a little dumb looking, but.
okay, so for T would be a 4x2, now that'd be a 2x4.
What do you mean?
So like T originally is a 4x2.
Okay, so you're gonna go here and here.
Yeah, so then there'd be 2 rows with 4 columns.
So you're going like this.
Yeah.
You're going like that. You're going here, 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 and here.
Yes, that should be the trend.
Okay, and how do the elements end up? So here's, let's say this is T1, T2, T3, T4, T5, T6, T7, and T8. And of course, we know that that is not the real element indices. I'm just counting.
So it goes, it's split, I wanna say it goes T8 first.
Here,
Yeah.
Oh, in the first column, it's T1 and then T2.
Here,
Oh, no, column. So it'd be going down. So T1 and then directly below it is T2.
good. Okay, so T1 is here and T2 is here. Keep going.
And then T3 and T4 in the next column, going down. And T5, T6 going down, and T7, T8.
Okay. So how did you do that transformation in your head?
I took the rows, I took each row from the original matrix and made it into its own column for the transfer.
Okay, good. Another way of saying that, and the way that I learned, which you're welcome to use either one, that's a perfectly good explanation. I start in the top left-hand corner. And I draw a line through what would be the diagonal of a matrix of that size. Right? And then I rotate around that point. So this becomes that. You see that?
I don't see this.
This arm,
Okay.
okay, rotates into place. You see that? Rotates into place. Yes or no? Good. This is the definition of the transpose. Why would you ever want to do that? That seems stupid. Right? That seems unusual. Who cares?
Another way to format a matrix, so that maybe you can like. Well, maybe you can like have it like, for matrix map, like just, multiplying it.
Yeah.
Isn't there like a rule that like certain like matrices cannot be multiplied by each other if they don't have like same like. Thing?
Well, before we go into like the real reasons why we're going to use it, right? Yeah, it's true that we can just transpose things if as long as we do it, in the same way in different areas. This is a tool for rearranging numbers, right? There's another one, which is called the inverse. What is that? What is t minus 1? Even when I told everyone to go back and read off their matrix section, they just said, well, because Monty will explain it on Wednesday. You trying to work it out? What's going on here?
That's a picture. No, I'm trying to explain it.
Okay,
Because I've seen it before.
it's just 3 characters altogether. No, it's not cheating.
He said, I'll look it up.
I didn't say look it up. I said you should have restudied this
Yeah.
before you came to class. So in fact, I don't want you to find the transpose or the inverse here. I want you simply to give you the definition.
So the identity is equal to t to the bigger.
Why? What does that mean?
That means because you have the actual like matrix, and you have inverse of that matrix.
Okay, that's the definition of the inverse, right? So t times t inverse gives you I. Why would you need that? I don't know, it seems pretty useful, right? We don't really talk about dividing matrices, do we? No. So in fact, T inverse gives us this, right? Okay. So These two things are gonna be really important, and let me explain why that is. Let's go back over here. Make some space. Um. We're going to be changing from one basis. So let's use the same basis, and we're gonna include the axes that are aligned along these directions. Okay. And this is like a really well drawn O in your book, and it's like not well drawn by me. But O is like the direction, with the basis space, okay? And we want to go from one coordinate space. And we'd like to transform by rotation into a differing coordinate space that we would call something like E1 prime, E2 prime, E3 prime. And that lives in its own OX1, OX2, OX3, where those are prime coordinate systems. Prime here just being a change from the original. Right? Okay. So let's assume that there is a transformation matrix. Okay? How do I describe, over here, I'm gonna have X, I, J prime. Oops. Xi prime. This is a vector in the new coordinate space, right? How do I describe it in terms of the old coordinate space?
Specifically for rotating?
Don't give me the components, don't tell me what's inside the vectors, just using our tensor notation. How would you write this?
Well, it'll have to be something like something times E1, or whatever our rotating factors are.
You said not to give you like notifications or like answers and things. Would it not be the difference of something and something else? Because it moved.
Yeah, so we're gonna see that if we write out the components. But the beauty, of course, of this section is that we're gonna stop writing out as many components. And those will be inferred, right? That's work to be done later on your own. So in fact, what I can do here is I can write a transformation matrix like this. Okay? And I'm gonna do that because it's a second order matrix. Okay? So Lij is our transformation matrix. And here I have to put what? X, but with what index? For this to be reasonable.
Would it just be I?
Well, this is xi prime equals Lij
So
x what? J. Why does it have to be J? Exactly. Because these are your dummy indices and they don't exist. So indices always have to match up on the left-hand side or the right-hand side, or what you've written is nonsense. Okay? Okay. So let's consider only rigid rotations of the coordinate axis. Okay? So we're going to say that L is orthogonal. What does that mean?
it's like each axis makes a right angle with the other one.
Well, this is the matrix. This is the second order tensor.
Oh,
I mean, it's one. Sure. I thought when it comes to matrices, the being orthogonal, it's like say it goes 1 0 0 0 1 0.
Ah.
Explain that.
Okay, so that's really good. So you have identified the identity matrix as being orthogonal. That's correct. But it's not the only one that's orthogonal. And in fact, the property of orthogonality is something that maybe doesn't come to mind because it doesn't feel like in your heart you would have to understand that. So orthogonal just means this. L inverse is equal to L transpose. Right? What does that mean?
Oh, wait. And that was, I was gonna say like, oh, then it's like a diagonal array.
Yeah, so in fact, we're gonna use one of these in a few seconds. So you're gonna see the rotation matrix and you'll see that it isn't only diagonal, but it will in fact be orthogonal. Okay? So the orthogonality of L, that is to say, the fact that this relationship is true, means that there are restrictions on what we can place into this rotation matrix so that it's still true. One of them is the following. Let me make sure I get all my indices right here. L I K L, oops, bigger if there's one. L J K equals delta I J. Also, L O I L J equals delta J. Okay. What did I write? Does that look like garbage?
Is that delta IJ?
Yeah, this is the Kronecker delta that we learned last time. So this one says that it's 0 unless I and j are the same index.
I just wanted to make sure that was an I, not just the weird accent.
Oh, sorry, yeah. This is the I, and that's the j. This one here, yeah. And this one here, maybe I'll make it bigger too. Sorry. If I had a paintbrush, this would go a lot easier. Okay, that's gonna look really obscure. I'm gonna write 2 more things on the board and we're gonna do an example together. And you're gonna be like, oh shit, that does make sense. Because generally speaking, when you look at this type of notation, it's helpful. It packs a big punch, but until you see it in index notation, when you see it written out in the matrix, you're not really gonna believe that that could possibly be true, right? Because what is this side here?
It's a 1 or a 0. Like, because it's a Kronecker.
Good, and just look here, where the I and the J. What rank is this?
Oh, second rank.
It's a second rank tensor. Right? You don't know what the dimensionality or how many, how big it is in either direction. But this is a diagonal tensor. With 1s along the diagonal and 0s everywhere else. And then this is some garbage that maybe looks a little obscure. But we see some repeated indices here, right? K is the same, so that's what you're summing over. And I and j here give you the rank of the tensor. Does that make sense? We'll see an example and then everyone will stop yawning, I promise. Maybe not. No, everyone is doing it. It's the morning and it's the week after spring forward. I've been asleep all day. This is coffee. Okay. So here's the last one, right? We're basically gonna say something that Lij is given by the product of these two vectors. That's gonna be the product of the basis vectors.
So that's EI prime?
Yeah.
Okay. Time E j.
Okay. Okay. So let's, I promised you the example would really help. And I hope that that's true. So let's draw it and we're gonna give ourselves some physical intuition for how we can construct out. So let's rotate a set of axes. Let's call this x1. Call this x2. Okay. And we are gonna rotate them. Here's O, the origin. Here's our new coordinate system, x1 prime. And here's x2 prime. And this will be the angle. theta. Right? So find out. Here's the hint. Right, on one side, your x prime coordinates in terms of your x coordinates. Hint, the third one is easiest. What? Nope.
Well, it's there, but it's not changed at all, so it just x prime 3 is equal to x3.
Correct, right? Because we're rotating in the XY plane. And I say XY plane, but you know what I mean,
A two-dimensional.
X1, X2 plane. But don't come after me in the comments on YouTube, because I know this is real big on YouTube. Yes?
I think I got it.
What's the third one?
Well, x three prime equal to x three.
Did everyone get that one? Good. What's the first one? Nope.
Just cosine theta?
Nope. Sure, it definitely has cosines and sines. But remember, how do we go about writing this? Okay, let's imagine some vector. B. So I am comparing, for example. This would be. The x1 component,
Oh, yeah.
and here. This would be the x2 component. Sorry. This would be the x1 prime component.
Okay.
Notice that the x1 prime component is not only in x1. It's also in x2, right? Depending on how much you rotate that coordinate system, you're gonna end up with a combination of both. So let me write it down. Is that okay? Okay. The first one is x1. And it's probably exactly what you would have thought it was. X1, no, keep going,
Oh, what x one?
correct. And the piece you were missing was
The x.
x2 sine theta. Right, the component that's coming up. And let's see if that makes sense. Okay, so let's not rotate it at all. Okay, so theta equals 0.
So theta equals 0, that's is 1, and then that's 0.
Good, that works. Now let's rotate it pi over 2.
Power 2, so that means.
What's that? This would be 0, right? And this would be
1.
there you go.
And then you rotate a 90, it's right on the x.
And so now you get somewhere in between at each time. So this coordinate transformation works.
Mhm.
Correct or not? Okay, what's the next one?
Definitely both.
There, it's not. Okay,
It's fine.
no, I was like scraping or something.
Yeah, it looks too periodic.
Yeah,
So with that one, is that just like, can we assume that it's like 90-degree difference?
what do you mean by that?
Cause like, that's what it looks like, it makes like a right angle. I was just gonna.
Oh, yeah, they definitely do make a right angle, right? Because it's a
Okay.
coordinate system.
Yeah, so we can just do what like. You know, we can't post my view. Oh, x2 prime would have like, cause it's in like the negative x1. Would it have like some,
Just x2 cosine theta.
You're saying it's the same thing?
Or the x1, x2.
Hmm. Bold but wrong.
but like, cause like the x2 prime is in like the negative coordinates. So like, if you're like going left. I was just like assuming that it's like negative x1, like in the negative x1 direction.
Mhm.
So like, I think it's like,
So you're saying something like this, right? So you're going. This is your x2 in the original coordinate system, right? And then this is your This is your x two prime in the new coordinate system,
Yeah,
right? Looks bad, right? So let's rotate those coordinates. Let's start in this direction. Okay? Not rotated. You need to get it back. So x two prime is gonna give you. Don't transform the matrix yet, right?
that's,
So you need at least x two, right? Okay, so we know there needs to be an x two, let's put it right here for no reason at all. What's the sign? It better damn well be positive, right? Because it's the same direction. Okay, now let's rotate it. And as we rotate it, what happens to each of those components?
they go towards,
Let's rotate it all the way down.
Every one side and cosine, it's going back down.
It's going back down. So which component is gonna go with x two here? Previously it was sine. 'Cause it was growing. This one is, it has to be cosine, because its maximum is at a 0, and it gets smaller until pi over 2 when it disappears, right?
oh, so then what x?
Right?
That's what I said.
No, that's only half of what you said.
It said x two cosine theta.
Okay, that's half of what you said. I wasn't saying you were completely wrong.
Oh, x one sine theta.
Okay, and that's where you're wrong.
You know,
It's
negative,
not.
it's negative sign,
It's negative sign,
because it has to be.
because it has to decrease. Very good. Okay. You're right, Reed. I mean, you're just not perfectly right. So then you're wrong. You know what happens when you build a plane and you're not perfectly right? The fucking wheels fall off, the door comes off.
In this bowling.
Yeah,
It's insane.
okay, all right, let's.
Looks like you end up in your car.
Okay. So, so here's our transformation. Okay, we struggled through it, but we got it. So let's write it. Show me the components of L.
So for x three, would it just be like? Would it be? I'm not sure if it should be 1 or 0.
Why are you saying x3? What do you mean by that?
Or like the third row? No, not the third row, the third column.
I don't know what you're saying, right? Are we talking about L or are we talking about X?
I was talking about L, like,
Okay.
oh, wait, you don't have to include x three because that's not being transformed at all, so we can just make this like a two-dimensional matrix. We're just like with like only featuring x two and x one, correct?
No,
Alright, disregard what I said.
we can't just change the dimensionality of a transpose matrix because we don't like how many items there are. You're on the right track, but you're thinking of it too much in terms of x1 and x2. I'm asking about L.
Hmm.
Here's another way to write it. Does that help?
Yeah, it helps.
So you need to see that in your mind's eye. Does that make sense?
Yeah,
Okay. So what's the matrix look like?
Just to, like for the top row, this would be what we found for like x one prime.
I'm gonna interrupt you again. I don't care about x's, I don't care about x primes. I wanna know what L is.
oh,
So you
okay,
just tell me each of the components of L,
I got it,
and then I tell you if you're right or wrong.
okay, so for-
Okay, so this is what I'm asking for, okay? What's the first one? And I'm gonna do this. Simplify it.
okay, the next one in the row is sign,
Zero.
Is that okay?
yeah, second row is negative sign, cosine. And then 0, and the last row is 0, 0, 1.
Okay, now we're in business. Okay, and if we had reread our vector calculus section, we would have done that in 2 seconds, right? Right?
Yep.
Okay, so now here's the question. Is this orthogonal? And what the fuck does that mean?
Oh, we got to take.
There's a possibility.
There is a possibility that it could be orthogonal. We saw that the identity matrix was already orthogonal. And we're not gonna prove that, but I want you, hold on, I want you now to prove to yourself, write it down. That L transpose equals L inverse. And let me give you a hint here. Okay? If this is true. Let me write it. If orthogonal, then T transpose T equals.
F equals the thing.
Correct. So do not calculate the inverse, because that'll take a long time. Just do that. And tell me if this is an orthogonal matrix. I realize that's really shittily drawn. But that's. Oh, what's going on?
I'm trying to remember.
It's like, no, no, so,
This. and added all the individual indices. This
Column times row,
column,
column,
column. That's the answer. Okay, folks, what's the first one? What's the transform?
Sine theta plus sin theta zero. Zero, zero.
All right, let's do every index here.
so for the first row of that one is gonna be cosine squared theta plus sine squared theta, which is equal to 1. Then it's negative cosine theta times sine theta plus, cosine theta times sine theta, which is equal to 0. And then 1 times 0 is equal to 0.
One.
Yeah, it should be, in that first column with the third row. Yeah, first column with the third row, cosine of 0 times cosine theta equals 0, 0 times sine theta is equal to 0, 0 times 1 is equal to 0.
You just know that because of the identity matrix, or do you calculate?
Well, I did the second row.
All right, so the first one is here. Minus sine times cosine, cosine times sine, they cancel. Second one. Okay, so did I lie? No, this is by definition orthogonal. Right? It has this property. Okay. Let's look at a couple more things because we're still getting used to how these tensors feel. So let's look at this weirdo thing that I wrote on the board and thankfully didn't erase. Okay, so Lik times Ljk. Okay. So let's pick an ij. Yeah, pick an ij.
What, 2, 3?
2, 3. Okay, so let's look. 2 over here. 3 over here. And what's that product? Because we're gonna have to sum over k, right? So we're gonna do L21, L31 plus L22, L32 plus L 3, 2, 3, L 3, 3. Okay, so where's L 3, 3?
That's on the bottom. Right, so it's
What's L 2, 3?
wait, so this is just L of like what we have.
Yeah,
Oh, okay.
we're just testing to see if this is true for this matrix.
Is it L 331?
Oh, you're right, sorry.
Okay.
Wrong one. Correct, entirely. L23 is,
That is 3-0.
okay, and this one, 3-2,
0.
2-2,
Which is cosine theta.
good, okay. And I was not equal to J,
Yeah, so
so
if
therefore that should equal
0, which it does.
amazing. Isn't that pretty? Didn't you love that? Wasn't that the best part of your day? Better than coffee? I mean, hold on, so like really sit back and think about this for a while, right? Because we created something, right? A matrix with, 5 elements in it that have meaning and a bunch of zeros. And yet it's properly constructed to describe this change of basis such that one, it's orthogonal. And it has that really cool property where it becomes the identity matrix, right? And then this really opaque statement that was made here due to the orthogonality bears out point by point. Every single piece of that second order tensor matches up exactly like this. Okay? So it looks silly, right? It looks like a bunch of busy work. But this type of these types of things that we're talking about, these tensors, the way we describe them, they underlie the fact that the physicality of space, the way that we describe the mathematics of our universe has very specific rules, and they're very robust, right? That make sense? Okay. Let's do one more set of things before I lose you for today.
And that held true because L was orthogonal.
Yeah, and we're gonna use L a little bit here, on and off throughout the discussion. Different types of tensors. Okay, so the first is the connection between first and zero order Cartesian tensor. So just to remind ourselves, what's a first order tensor? Cartesian?
There's this vector.
That's just a vector. An example of that would be velocity. Good. And what's a zeroth order tensor?
Simply a scalar.
Good. An example of that would be? Okay, not a good example, but go ahead. A number is not just a scalar, right? It is true that that is a unit, but we're physicists. Some of us are. Maybe we don't all identify as physicists. Maybe some of us are astronomers or nuclear scientists, but planetary scientists. Pretty easy. Any scalar will do.
Except for 5.
Except for 5. 5 won't do. What's a scalar? Mass, good.
Speed,
Okay.
volume.
Volume, those are good scales.
Okay.
Right? Time.
Mhm.
Time's a good scale. Okay. So in general, we saw that we could go from one group of these zeroth order tensors into the first group. Okay, how do we go from a zeroth order tensor to a first order tensor?
Well, you would just add. You can add an index to it.
Nope.
We're going in.
What's that?
Give it a direction.
Yeah, I mean, you can arbitrarily just draw a little arrow over it, but that's not what I'm asking. Right? Going between speed and velocity is drawing an arrow over it. That's not what we're asking. We want to think deeply here. We've seen these processes before in our life. go from a 0th order scalar to a vector? Please.
Well, there would need, we need like some sort of like a coordinate system to like,
We're already living in 3D world,
okay.
3D Cartesian.
Okay.
We're not gonna describe bases anymore. I want you to think back in your personal history with mathematics. And what operation takes you from scalar to vector?
The ones where we have this like, speed, like. Adding to the direction and then the X something.
Oh, you're still.
Oh, is it deeper than that?
No, cause like, I think Reed's on the right track with like a curl. So I
No, hold on,
Yeah.
Reed is not on the right track with the curl,
Sorry.
because what is a curl?
A curl change to something, I wanna say that before.
What? No, tell me what the curl looks like.
It was, so it's a gradient cross product with, then a vector.
Okay,
Yeah.
so please tell me here,
That's right, but it's a scalar.
does it?
No. So it's so much harder.
It's a vector and a vector. It makes a vector. What did I ask for?
Oh, wait. Oh,
Yeah.
so the dot, wait, so a dot product. Is it a dot product?
Well, okay, so now we're thinking about our different stuffs, right? Okay, so let's, you're not answering the right question, but you are answering the question that I haven't posed yet.
Okay.
What? Let's do what you said first.
Yeah, so the,
So,
I didn't say divergence. Did I say gradient?
No.
okay, so now we're throwing all sorts of stuff around. Do we want to answer this question or do we want to answer the one you just posed?
Let's do one at a time.
I think it's.
You think it's the gradient? What is the gradient operator look like?
It's like,
It's d over dx1, so it's that.
and then it's a scalar.
Oh, the scalar, like I asked for.
Yeah.
Oh, amazing. Okay, what is that equal to?
D over dx1,
No, simple.
okay,
Right?
Okay.
So how do we go from a scalar to a vector? Well, we can use the gradient operator. Good. And if I write this in terms of tensors, because we're no longer children, we're big adult people. Okay, how do I write this?
so this one.
Right.
Theta,
Theta.
whatever. the-
That's tensor notation. Beautiful. Isn't that gorgeous? Isn't that the best thing you ever saw today? Second best thing after this, right?
Oh, yeah, why is it negative?
Well, just mathematically speaking, the electric field is the negative gradient of the scalar.
Oh, you're right.
Just because that's convention.
You're
If
right.
electrons were positive, then it wouldn't be this way. Okay, so good, that was wonderful. Now let's go backwards. So let's go from first order to, oops, I didn't finish that, to 0. Quickly, folks, you already said this, you already.
Oh, the divergence. Is it the divergence?
Already said it, you've already seen it. It's not the divergence.
Oh, dot product,
The dot product.
dot product.
Okay, how do I write that?
In matrix or just like, you want a matrix notation or just like regular?
You're saying matrix notation, but we're not using matrix notation, we're using.
Tensor notation.
Yeah, it's easy to confuse them, but remember, when we're using dual index notation. That's actually different, right? So this right here with the L like that, with the indices, that's matrix notation.
Okay,
If I do the same thing like this. Right, that would be tensor notation.
okay,
So here I like it in tensor notation.
so you want that in tensor.
What? You have to put a dot?
I think it's.
No, you don't have to put a dot,
Why?
because now it's fucking sick, bro. Look, that's awesome. Okay, and now what?
Is equal to, just whatever symbol you want for the scalar.
Yes. So I'm gonna put something like C. And I'm gonna put no I's. Right?
To show that it's a scalar with zero rank.
Exactly. Okay, so now we've seen how we can go between them. So this one here, what was this called? What was this property? The gradient. So this is the gradient operator. And it's not alone. Let's see other versions. This one here is fun. I'm gonna give it a new name. Okay. You have heard it called the dot product. That's perfectly fine. We're gonna call it the inner product. Cool, right? Everything gets a new name. You get a new name. You get a new name. Okay. So now we get to talk for the first time about second and higher order. So, okay. We get to define second and higher order Cartesian tensors. Okay. We're gonna have fun. So everyone's remembering what L is in their mind, right? Excuse me?
Yes.
It's easy now, right? Once you see L, you can never unsee L. Okay. So let us define then some Cartesian tensor. Second word. Okay. And I'm gonna call it T I J. Okay. I'm going to let it transform. Okay, L K I L L J T K L. Okay. And there's another way to do that, T prime to the. So what I mean by this is that I can have some tensor, second order tensor, and I can transform it into a new basis set using my rotation matrix. Does that make sense? Some property of the system, I rotate it, and I still have that property. Those that are unchanged under rotation are considered invariant. And we'll see examples of invariance when we start to talk about these things in earnest. Okay? We already talked a little bit about the matrix notation here, but I'll just say it so it's clear. These are rows. And these are columns. Right? We already knew that. Okay. So not all linear operators are second order tensors. And what I mean by that is here LKJ or KI or LJ. These transformation matrices that you just saw, they were second order operators. But you can have a linear operator that transforms a vector into a different vector space that is not a second order operator. Okay. So let me give you an example quickly of a couple more things that we did. We saw the gradient operator over there. That will allow us to move up in order, going from 0th to 1st. But you could just as well imagine operating on a second order like this. How would that work? What would I write?
you repeat the question?
So let's say I take a vector. And I take the gradient of the vector.
Okay.
What do I get? Let's first write it in sort of normal notation.
We have scale.
Excuse me?
Oh, you can-
I heard scalar and I heard matrix. So which of you is right?
Oh,
The
wait,
gradient of a vector,
Yeah,
Don't go out.
well, you tell me. You've done gradients of vectors, no?
Oh, yeah.
How do you do it? What does the gradient look like?
D over dx. Gradient of that, and then whatever vector, so like u. And that's equal to, and we're doing normal notation, d over dx, bx hat.
That would be the divergence. Notice there's no dot.
There's no dot, huh?
Divergence goes down, right? That's the inner product.
Oh, yeah.
Have you ever actually done this?
That's true.
The gradient of a vector? You may not remember this. It's actually not as obvious as you think it is. You've done gradients of scalars many times because that ends you up in a vector space, but you may not end up in a matrix that often. So let me show you how it looks. Okay. Let's write this in our tensor friendly area. Okay, I'm gonna write d dxi v j. That is our new t I j. You see? So let's imagine a 3D coordinate system. What would that look like?
start with like the number one, so you.
Oh,
Yeah, so these would both be 1, right? And you could do something like dx1 v1. And I know that was horrifying, but that's gonna save me a lot of writing, so we're gonna do that, folks.
oh, so then it'd be dx2 v2 for like the second, in that column, in that row.
v2,
Yeah. Oh,
v1, okay?
Yeah, sort of reading.
Now we're cooking with smoke,
Okay.
right? Now we're smoking. And you could keep going, but I'm not gonna. Does that make sense? Does it make sense? Good. So the gradient operator still works here. Okay, I taught you about the inner product. There must be an outer product. What the fuck is that? Okay, so let's learn the outer product. And this one I've already heard today. Curl, very good, except for not. Just kidding. So it's not quite the curl because the curl uses a specific type of operation in the outer product, and the outer product is more general than the curl. But it's the right idea, you're just missing one thing at the beginning. So the curl is del cross something. The outer product doesn't require the del. It's simply the cross product of two vectors, but in any dimensionality of space. So I can do an outer product between two tensors. Right? That's gonna fuck your brain up, but that's okay, because that's how cool this space is. So first tell me what the outer product looks like in terms of two vectors. How would you write just the cross product, for example? Yeah, that's okay.
Put that in on one paper. and it's-
Oh, you really in my backpack?
Yeah, that has all the identities for curl.
Oh, I don't.
No. Just the simplest version possible. How do I write, not the curl, I don't care about the curl.
Yeah.
How do I simply write a cross product? Cross U for V for me, what am I writing?
Wait, yeah, we cross it.
U or V cross U, right? Good. That is the outer product in vector form. But in better form, how do I write this? It is super easy. Yeah. Yeah, so I'm gonna do V because I did that first,
Yeah.
and then I'll do UJ. What? Grismani, shut up! Okay, and what is that equal to? Well, that is our new tensor Tij. Notice the difference. The outer product takes two first order vectors and gives you a second, sorry, let me say that again. The outer product takes two first order tensors and gives you a second order tensor. The inner product takes two first order tensors and gives you a zeroth order tensor.
Okay.
That makes sense?
Okay.
Okay. Okay, all right, I held you for too long. Thank you for sticking with me there. We're going a little bit slower than I would have thought. So if you are reading along at home, stay in the tensor region right now.
Okay.
And really make sure that you're brushing up on what we're talking about here. We're gonna end up, hopefully by the end of next Monday, in something called the Levi-Civicci tensor. It's fun. It's a tensor of third rank. It'll be the first one that you see before we head off in the direction of special relativity. So as soon as you get to the Levi-Civita tensor, you know, you can kind of like slow down on your reading and maybe read Griffiths a little bit instead.
Okay.
That make sense?
Yeah.
Read whatever you want. You can read both. You can read this, you can read both. I don't care.
Do you have any more?